Now.
Look at my screen. I've been trying to fix it all day.
Now?
It's not working.
Yeah.
Are you featured? Are you featured?
Yes.
I did. We're standing here.
Why is your head so much higher?
What? Oh my God. Go normal? Now come to my level. What are your tippy toes? It's okay. Okay. Have a great day, guys. Oh! He's gonna send this. He's gonna send the email out with the video, and it's gonna be us.
I got them all cut.
Oh. Okay.
Except for like 2 of them that my wife pointed out that I had to fix it. She's like, I think you missed a couple.
This is so funny.
Chemistry fun? That's all I do. My whole class.
Did you get the little stats when you came?
Oh shit, she put the grades in?
Yeah.
Wait, how many points is that of?
3.
Oh, that won't take a huge hit, right?
No, it doesn't change it.
You know what this is?
That's why you got 0.
2, buddy.
It's actually a crystal structure.
I got 3.
I just wanted to make sure that was crystal.
Did you go? I think it's in the bag.
What the fuck? Huh?
In the bag.
You didn't say a good one.
Well, you didn't
Oh!
tell me.
Oh yeah, that's your.
Is that yours?
Well
No,
done.
let's not. Actually, how does he get it so much?
Very good.
I think that's something we gotta start.
Wait, Josie, no, let's not. I am so No, submit them to that. Shut the fuck No! I will actually start crying. I can never show my face when you come to your ass. Who is it? Oh my god, bro, she can have it. She can have it. I don't I actually like
Who?
9.
Oh, that's Miller.
Who?
I'm going to kind of review the rules we applied last week to write the Lewis structures. I don't expect you to be an expert yet, but by the end of today you should. Okay. But this is important because it's really basis of all the other parts in covalent bonding that we learned. So if you're not good at this, it's going to kind of mess you up going forward. So remember, when we're building these structures, we have to count the valence electrons, arrange and bond the atoms at least with one bond. Then we satisfy octets, meaning take the electrons that you have left and try to give everybody their full octet. And then when you can't do that, there are 2 possibilities. If there's too few to do this, maybe this should be a subset of point number 3. So if there's too few, that's when you do multiple bonds, like double and triple bonds. If there's too many, meaning we go past octets, we do extra pairs on the central atom, which presumably is one that can be an expanded octet, right? So in the 3rd row or later. And in essence, this should pretty much cover it. The only thing we didn't put in here is when you're counting valence electrons, don't forget to account for if there's charge. Meaning if they're positive or negative, we have to put extra electrons in or out. But this is a basically truncated version of what we were doing. So the only thing we have to be careful of here are the built-in exceptions to the octet rule. So I'll put that out to the, well, I'll put it in this direction since you got to be in the camera. So exceptions to remember are beryllium. Well, I'll start with hydrogen. Hydrogen, beryllium, and boron. Other than these 3, you should try to fill all the octets. With these 3 elements, hydrogen, instead of an octet, picks up 2 most. Beryllium, 4 electrons, and boron, 6 is fine. Therefore, remember, anytime I'm saying octet, I'm expecting 8. Those exceptions allow there to be less than 8, and that's okay. Yeah, I think that covers everything. So what we're going to add to the picture today, which will come naturally out of this review, is the concept of resonance structures, which we need to understand. Lewis structures are pretty good for what they do, but they have limitations. But let's let this happen as we go. So were there any of these problems you wanted me to kind of work through with you as examples? Jason, got a picture.
That's 6.
Ah, good one. Do you mind if I don't have the screen up? We don't really need that in our face, right? Whatever you call out, I'll just do. So I'm going to kind of run it next to the rules so you can see how I'm applying these rules. So first I'm going to count my valence electrons. Sulfur has 6. Each fluorine has 7. When you add that up, that's 48. That's a lot of electrons. Now, here's the first thing you have to see. We have made the argument that we should typically put the odd atom out in the middle and attach everybody else to that. Well, that means we're going to actually get 6 attachments to the sulfur here. And that's okay, because we're allowed to hypervalence the sulfur. We're allowed to go past the octet rule for sulfur. We don't force it to, but when it has to, it's allowed to. So this is how the attachments will look. And then you can see that every other fluorine, or every fluorine really, is going to need the octet. So I have to go around and just zap in those electrons. So once this is done, the sulfur has 6 pairs or 12 electrons around it, which is okay. Each fluorine only has 8. And the total picture, if you think about, there's basically 6 units of 8, that's all 48 electrons. So we've matched every rule and found the right picture. Okay, go ahead. That's a fun one. I'm going to leave this one up for a minute because it's going to fall under my resonance structure argument. Kind of. Yeah, I'll take it off and can put it back there. All right, so that was the C2H5OH. Yeah? I think you could have found more than one way to obey the rules, but now we can see why some of these formulas are written in a weird way. Like, why did they separate the H's the way they did and stuff like that? They're trying to convey the way atoms are actually laid out in this molecule, particularly because there's more than one way that it could be done. So I'm going to build it the way it's intended, but this is going to have a carbon-to-carbon backbone, and then the oxygen's going to attach to one of the carbons. There's no real much choice here because the hydrogens always have to kind of plop around the edges. They can't be in between. So I'm going to build it this way, and then I'm going to ask if you can see another way it might have worked. But if I do this, I can see that there's going to be 6 hydrogens. There's 3 of them. There's 2 of them. And then the last one can attach to the oxygen here. Oh, I forgot to count my electrons, sorry. 8 plus, well, I'll just add this up, 6 total hydrogen. And then the 1 oxygen. So 12. Is that 20?
Yeah.
So let's see what we have so far. 2, 4, 6, 8, 10, 12, 14, 16. Where are we going to put the other 4? Jason, where do we need them? Which atom is not satisfied in my picture? Yeah. So 2 lone pairs on the oxygen atom, and we've built what this is trying to convey. Just double check that each atom is satisfied. All the hydrogens are good. The carbons each have 8, and so does the oxygen. Yeah?
So, like for the SF6, you can just put like however many electrons are in it.
In general, that's correct. If that's called, I mean, there's no other choice there. There kind of is, but I'm going to show you why it's not a real choice other than that. Now, did anybody come up with a different version of this by any chance? Another way that could work? Because I can think of one more way we could build this and still satisfy all the rules. Do you see one quick, simple move that might allow me to do this another way? You just switch one position, kind of works. That's all right, I can show it to you. What if I swapped the position of the carbon and the oxygen? Then it would have looked like this. And I think if you look at this, you will find it has the exact same properties except where things are attached. This has 6 hydrogen, 1 oxygen, and 2 carbon, and it has the correct number of electrons, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. In fact, both of these could really just be written C2H6O. They both have that formula. But if I wrote that, you wouldn't know which one I meant, would you? So the way this is written kind of conveys that the OH is stuck to each other. Whereas if I wrote this in this kind of condensed form, I might write something like this. So you're starting to hopefully get at least a little taste of why do we write it in a weird way when we can write it in a simpler way. What we're calling the weird way kind of conveys the difference between what are called structural isomers. This is an important term in organic chemistry that I'm introducing. You don't really need to know it here, but I think it's worth knowing. When you're looking at structural isomers in organic chemistry, or really in any chemistry, you're looking at something that has the same chemical formula. So all the numbers and kinds of atoms are the same, but it has a different bonding arrangement. In other words, the atoms are bonded to different atoms. So structural isomerism, obviously as the molecules get bigger and there's more atoms, there's a lot more different ways that we can put them together. And those different isomers exist. They're real different molecules with different properties. Anyway, I digressed a bit, but that's all. Any other ones you want me to go through?
The CLF3.
Ah, that's a fun one. CLF3. What did you think to do with it? Like, where did you start?
Just I put a CL in the middle and then I just branched out to the 3 Fs.
Very good. And how many valence electrons are we supposed to have here?
28, I think.
Agreed. So you satisfied all these guys?
Yeah.
And then you found out you had an extra pair, right?
Yeah.
So it just goes on the chlorine, that's the middle atom.
Okay.
It's a 3rd row atom, and therefore it can do that. Are we getting the hang of it? Are we seeing how it's coming together? I don't know. You got it, Tilly? All right. I want to get into one of them that specifically I think we need to understand something about, and that's the carbonate, the CO3 minus 2. So I'm going to do that one with you here, and I'm going to use it to start explaining what resonance structures are. Man, Lewis, for all his genius of putting this little system together, couldn't have picked a worse word than resonance structure for what I'm about to show you. It's like literally the antithesis of what he should have said. Anyway, we're going to break this into 2 categories. There are what we call equivalent resonance structures, and that's what I'm going to cover first. Meaning that I can draw the same molecule multiple ways by just pushing electrons through it in different positions, but it always looks the same somehow. The other type of resonance structures are non-equivalent, meaning that one is the best one out of all of them. And we need another parameter to judge this. That parameter is another piece of lesson that we call formal charge. So I'm going to kind of methodically go through this with you, try to get the idea in there, give you some problems to try. And then if we need more time to mop it up tomorrow, that's fine. But my big push for tomorrow is going to be Vesper. We need to kind of get through the shapes, the 3-dimensional shapes of molecule stuff, at least tomorrow. Let's at least set it up. All right. So my example of equivalent resonance structures right now is going to be through the use of the carbonate ion. So that's an example. So if we were building the carbonate Lewis structure, we'd start like we always do. Count up our valence electrons. 4, 3 6s, and a 2, and the 2 electrons that we've added. That's 24 valence electrons. We would bond everybody to oxygen, to carbon, like that. We would satisfy octets first for the outer atoms. And now we would say to ourselves, we have a problem. And the problem is what? Who? I heard a voice in the distance. It was a weak and quiet voice. For who? Carbon is short. You shafted carbon. Doesn't got is 8. You can't just move in new ones from nowhere, but you can double up, right? This is where we get into this rule of if you don't have enough to get everybody satisfied, you look for multiple bonds. But here's the problem. How do we pick which one? It doesn't matter, you're right. But there's another problem. If I simply pick one at random and say, there you go, there's my Lewis structure, that's correct, but it's also wrong. But it's not your fault, it's Lewis's fault. Here's why. We can measure what is called bond order, which is a measure of strength. It's just the number of actual bonds, so to speak. And we can also measure bond length, which is literally the distance between the atoms that are bonded. And we can also measure bond enthalpy or bond strength, bond energy, however you want to say it, like how strong the bonds are. These are basically the same idea. Here's the issue. The stronger a covalent bond, the shorter it gets. Because if they can pull together tighter, they're going to get closer to each other. So if I look at the general length and strength of bonds, if I go with a single bond versus a double bond versus a triple bond, and again, this is strictly for covalent bonding. As I go down this list, here's how my bond order goes. This would be 1, 2, and 3. That should be pretty obvious if we're just counting the bonds. But in terms of strength, and in terms of length, and of course I just ran my table together into my example, which of these is the strongest?
Triple.
The obvious one, right. So this is the strongest, and single is the weakest. Obviously that falls in between. So what would be the longest bond based on what I just told you? Which
Is one.
Yeah, the weakest one, right? That's going to be the longest because it's less pulled together if it's weaker. And the shortest bond will be the triple. So the reason for me telling you this is if this were the true structure of carbonate, doesn't it suggest one bond would be a lot stronger than the others? And doesn't it suggest one bond would be shorter than the others? It suggests there'd be a bond of bond order 2 and 2 bonds of bond order 1. But that's not what we find. This is what Lewis's picture says, but the reality, unfortunately, isn't that simple. It turns out that the reality makes all 3 of these bonds equivalent. All 3 bonds in carbonate are the same. But that's not strange enough. The stranger part is the strength and length that we measure in this molecule is such that it seems to suggest a bond order of 1 1/3. What? How do you get what? And so that's really hard to fit into the Lewis picture. How are you supposed to show 1/3 of a bond and somehow being shared around 3 places? Well, here's what Lewis came up with, and somebody should have slapped him in the head when he did it. Here's how Lewis represented this molecule to account for what I'm saying. Because it's not a double bond and 2 single bonds. It's 3 equal 1 1/3 bonds worth. We will understand that better when I put the orbitals into the picture next week. But for now, Lewis had a problem, and this is how he solved it. He said, okay, we have this situation, we just have to show all the possible valid structures that we can as a series of structures where all we're changing is where that double bond is going. And then of course we have to adjust all the lone pairs as we go. So we could have drawn it this way, right? And the third way we could have drawn it was this way. Now, why am I saying all of these resonance structures are equivalent? Why am I saying they're all the same?
They're all equally right.
Yeah, they all basically are just taking a double bond, or could be a triple bond, and just rotating it through 3 equivalently well, just equivalent positions, because all the oxygens are the same. There's no reason for this bond to form here versus here versus here. It somehow forms across the entire space. Again, the Lewis model can't do well with that. So he did this. Now here's my point. These resonance structures fall under the equivalent, but the only proper way to represent carbonate is that way. Does that mean all three of those exist and the bonds going? No. That's why this is stupid. Because resonance sounds like something's ringing back and forth, right? This is not that. I'll show you what I mean. I shall now draw a resonance structure for you, genetically. This is a resonance structure of any child based on genetics. How do you interpret this diagram as being you as a resonance structure? What am I saying? Am I saying you're flicking between literally being your parents? Like moment to moment, are you mom then dad, mom then dad? That would be awkward. So what am I trying to say?
You're a combination.
What?
You're a combination.
Yeah, you're an equal blend, genetically at least. So your reality is really just a mixture of those two things. That's what Lewis came up with to fix this problem in his model. Because this could have gone three ways, and the measurements actually show what looks like an average of 4 bonds over 3 spaces, he's saying draw all the possibilities that are equivalent and average them. That's what this is. Now, that's a pain in the butt, right? So when you're doing it on homework for me, it's enough, for my purposes, if you draw one and then just write res underneath so I know you know that. That would be good enough for me. So if you're looking at your paper right now, and you did carbonate over the weekend, and you drew one picture, I would add to that box the word res, and if that's not enough to link you back to what I just did here, draw all 3 images so you know what I'm asking about. Again, resonance is the worst word you could use for this in this context, but there it is, folks. So how am I going to know when I need this? Let's look at a couple examples of yes and no. If I wrote the structure for HCN, I have 10 valence electrons. Ooh, there's a triple bond in there. Is this going to need any kind of resonance picture? Are there more than one places that triple bond could go that's equivalent? No. So this does not require any kind of resonance. Right? It's irrelevant to this picture. So you would not use resonance for this. But what if we were looking at one that, I don't know, looks something like this one? Let's do ozone. Ozone simply has 18 valence electrons. So when you try to build ozone, I'll do it up here, you get something that looks like this. 2, 4, 6, 8, 10, 12, 14, 16, 18. Oh no, I ran out of electrons and I don't have octets everywhere. What will I do?
Make more bonds.
What?
Like, add more bonds.
For which side?
Either.
Exactly. See, this time I have to do both. I'm forced, because it could be equivalently done on either side, to show resonance structures. See, both of those are equivalent pictures, but the reality is they're average. So if I ask you what's the bond order in these positions, what would you say? How many bonds are there really in those 2 spots? It's not 2 and it's not 1. What is it?
3.
It's not 3, 1.5. It's the average of the pictures. You're averaging 3 bonds over 2 spaces. It's like showing 3 candy bars with 2 people. Everybody gets 1.5. So the bond order here would be 1.5. And that's enough to tell me that that bond would be stronger than this one, because this is only 1 1/3 bonds. And so, again, you have to kind of make that comparison. All right. Now I want to show you another interesting case where they're not equivalent. For these, you don't have to automatically write resonance structures. but you have to tell which is the best one. A case of non-equivalent resonance structures can be done with a simple molecule like carbon dioxide. So let's do the carbon dioxide picture, and then we can start expanding on the idea of how does formal charge help me tell the best picture. So if we were doing carbon dioxide, we have 16 valence electrons that we have to put into the picture. Theoretically, the most simple way to symmetrically arrange this would be like such. And then we'd start satisfying the octets of the outer atoms. Uh-oh, I used up all 16. But carbon's short a lot. Now what do I do? How do I fix this?
Add more bonds from both sides.
You want to do it from both sides? Like that and like that? That looks good, it's symmetrical, it's pretty, and it works. But wait a minute, I have a positive question for you. Why couldn't I have done this? Does this violate any rules that we've talked about?
Yeah.
2, 4, 6, 8, 10, 12, 14, 16, that's still good. What rule am I violating? This has 8, this has 8, and this has 8. Both of these pictures satisfy all the rules. But I'm going to tell you one is better than the other. What does your gut tell you is the better one? Why? It's about right, yeah. It's more symmetrical, right? But we have a method, a test, that sounds a lot like something we've done before. Remember oxidation numbers? Oxidation states? Redox? Well, those numbers we used to guide, at the time, just our balancing and really to keep track of the flow of electrons as a certain type of chemical reaction was taking place. In this case, we're going to use something that sounds very similar, but it's called formal charge. Formal charge is kind of a way to figure out how stable your Lewis structure is. It's also a way to figure out in a molecule where there's centers of positive and negative charge, and actually in organic chemistry you can use that to predict certain types of reactions. But anyway, here's what I want to show you. There's a way to calculate formal charge. What we're really doing, let me write this because it sounds pretty, and I want to make sure I'm going to get rid of this part for now. So formal charge, heretofore to be abbreviated FC, is really just comparing the electron environment, if I can use that term, meaning how many electrons are around me, of an element in isolation, meaning as it would be by itself, versus in a given compound. And the goal here, the idea here is the farther away we get from our kind of normal electronic environment, the less stable the situation becomes. Because what that's saying is electron density is being shifted away or toward beyond what we're used to. So here's how you calculate it, and then I'll show you the simple way to do it. You can find the formal charge on any element in a compound by simply taking the number of valence electrons it would have when it's alone, meaning from the periodic table, and then subtracting how many valence electrons it has kind of in the molecule. But to calculate this, we have to count them a certain way. So, in the molecule, any lone pair electrons, in other words, electrons that I own to myself, I count all to me. So I'm going to count the number of lone electrons that I am holding, and I'm going to add to that half the shared electrons. But there's an easier way to count half the shared electrons, right? Isn't it just the same thing as the number of bonds? because for every bond, we're sharing 2 electrons. But I get half of that. Therefore, I get 1, which is just the number of bonds. So all I'm saying is, in this calculation, you can think of it as half the shared electrons. But that's the same thing as saying the number of actual chemical bonds. These are the same number. Okay? Now, all that looks like an equation. You don't need the equation. Let me show you the easy way. So before I do my actual example, I'm going to use water as an example. So here's the Lewis structure of water. If I wanted to find the formal charge on the oxygen, the first thing I would look at is, well, what's the normal valence electrons on oxygen? Isn't it normally 6? But in this molecule, it has 1, 2, 3, 4 of its own electrons, and it has 1, 2 bonds. So in the parentheses, it adds up to 6, and the difference is 0. So in this molecule, oxygen has the ideal situation. Its formal charge is 0. That, in general, is the ideal case, because what you're saying is that atom's in an environment electronically that matches what it's used to when it's by itself. Each hydrogen, you shouldn't even waste your time. Hydrogen's always going to have a formal charge of 0, because it can never do anything but make a bond. So the calculation will always be 1 minus 1. Which brings us to a very similar formulation that we said for oxidation numbers. The sum of all the formal charges in a molecule still has to equal the net charge. Okay? Now, let's go back to carbon dioxide and calculate all the formal charges and see what conclusion we make. Now I'm going to show you the easy way. Watch carefully as I do this. I'm going to use what I call the countdown method. If you see it once or twice, it'll become so easy, you'll just do it instantly. What's the normal number of valence electrons for oxygen?
6.
6. Now watch how I'm going to subtract from that. For every electron it has on its own, I'm taking 1 away, and for every bond. So if I start with 6, and I start counting down, I take off 1, that's 5. 4, 3, 2, 1, 0. Formal charge here is 0. Let's do it for carbon. What's the normal number of valence electrons for carbon?
4.
4. I'm going to subtract off 1, 2, 3, 4. So that's 0. And this oxygen's in the exact same boat as this one, and it has to add up, so this is 0 too. In other words, what we see here is that every single element in this arrangement has a formal charge of 0. You can't get any better than that. That's the ideal case. But now let's see what would have happened had we done a triple and single bond, which doesn't violate any of our other rules. Well, this oxygen normally has 6 around it. 5, 4, 3, 2, 1, 0. Take another one off. Here it's -1 formal charge because of that extra electron around it. This carbon's still 0 because it's just got 1, 2, 3, 4. And this oxygen, which starts normally with 6 around it, only has 1, 2, 3, 4, 5, making it +1. Which of these two pictures looks like a better, more stable arrangement? Which one's the better one? Well, I haven't really told you, but here's the idea. In general, you're going to look for the structure, the Lewis structure, that minimizes the formal charges is usually going to be the best one. Now, that doesn't mean the sum of them, because the sum of them is always going to come up the same if you did it right. Notice the total here is still 0. So we want the fewest formal charges throughout the molecule. That's better than having more. And the lowest, meaning lowest in size. In general, the Lewis structure, if there's more than one valid one that doesn't violate any other rules, but the Lewis structure that minimizes the formal charges will be the most stable one. What if it's a tie? So after you look at just this, the next thing you look at is electronegativity. So you should look for negative formal charge should be on the more electronegative atom. If you have to kind of come to that tiebreaker. And I have one example we can work through a bunch of possibilities to show how all this works. But before I do that, I want to show you another situation. You asked me for a sulfur hexafluoride today, remember? And we drew this. There was 48 electrons on it. By the way, a really important fact about resonance structures, you better get in your head right away. Resonance structures have to have the same atomic arrangement, meaning who's bonded to who doesn't change, just different electron arrangements. All you're allowed to move are the electrons or the number of bonds or the lone pairs. You can move them around. You can't change who's attached to who. That would cause change in isomer. So different electron or bonding arrangement is fine. So what you're really doing is just pushing electrons around the same picture. Now, even that, though that's true, I'm going to show you we can use formal charge even more beyond just resonance structures. Check this out. I could have tried to make SF6 this way without violating any of my rules. It would have all the same number of electrons and all the same number of atoms. But why this is not as good as this has to do with what formal charge tells us. In this picture, every fluorine and every sulfur, the only sulfur, all have formal charge of 0. But in this picture, this sulfur, and again, we can prove it by doing really simply, what's the normal valence electrons of sulfur? 6. And then we just count off the bonds and the lone pairs. 6, 5, 4, 3, 2. That means the sulfur here is +2. The fluorines on the outer are all 0 because you start at 7, 6, 5, 4, 3, 2, 1, 0. Just count them down. And then the fluorines in the center, and this is the part that starts to get weird, would be start at 7, 6, 5, 4, 3, 2, 1. +1 and +1. Now look at that picture. That should make you want to scream and take like a dirty, rusty scalpel and gouge your eyes out. Why should that picture look so unstable and stupid the way I just drew it? Look at what's happening. 3 atoms in a row, 2 of which are fluorine, the most electronegative element, have positive formal charge right next to each other. That's such a high energy and unstable situation. It's like trying to push 2 north poles of a magnet together. They just push apart. So that's why you can see the formal charge concept can go even beyond just evaluating resonance structures. It can even tell you, yeah, this is probably not a likely arrangement of atoms. It's not going to be stable. I'm afraid that you're not catching my formal charge concept easily, though. Am I wrong? Yeah.
Wait, is it also wrong because it's formal charges? I mean, the net charge is 3.
Well, that's another problem. That totally blows it even further, doesn't it? Because it doesn't even make sense. So I probably missed a bond somewhere, or maybe I counted the electrons wrong when I built it. Because that shouldn't happen anyway. If I did it, let's see, 2, 4, 6, 8, 10, 12, 14, 16. Oh no, it's all good. Yeah, it's just that's bad. But that shouldn't happen, so clearly there's a problem there too. But I just want to make sure you're all catching on to how I'm doing this countdown thing. Because you can use this formula, it just seems like a waste of time to me. Because all you're saying is, if I'm, let's do this one. Thiocyanate ion, for example, right? Oops. When you look at this, to find the formal charges, we're just trying to ask, how many electrons does it have now compared to what it has when it's by itself? And if it helps you to visualize it better, let's expand the bonds for a minute into dots. See, the whole point of covalency is we're sharing electrons. So here's how I'm counting the dots. This sulfur kind of gets to claim that many for itself. This carbon gets to claim this many for itself. You see what I'm doing? I'm splitting the electrons for this purpose that we're sharing. And the nitrogen gets to see these. Now, sulfur normally has 6 valence electrons, but look in this picture, it has 7. It's got 1 more electron than normal. That's why its formal charge is -1. All I was doing is saying, okay, start at 6 where it normally is and just start subtracting the ones that it has around it. 6, 5, 4, 3, 2, 1, 0, -1. And that's how I get there. Carbon normally has 4, and this carbon has 4. Nitrogen normally has 5 valence electrons, and this nitrogen sees 5. So it's right where it should be. But what's kind of cool about this is if we start looking at atoms, there are patterns. There are ones that absolutely will not go past 0 formal charge, like fluorine. Fluorine, because of its normal valence structure, only ever makes 1 bond. Because if it started making more than 1 bond, it would be sharing more electron density with other atoms, and it would become more of a positive formal charge in the molecule. But why would fluorine share with anybody? It's the most electronegative element. So, again, if you start from the normal atom, you can see how many bonds it should tend to make to have a formal charge of 0. Oxygen. How many bonds does oxygen going to make to maintain a formal charge of 0? What do you think? 1, 2. It can make a double bond or 2 single bonds and still be formal charge 0. If it makes a 3rd bond, the more bonds I make, the more of the electron density I'm sharing, the more positive I become. If I take more lone pairs in, now I have a lot more density around me, and I become more negative than my normal formal charge, or my normal valence situation. So here's the skills you need. Not only how to write Lewis structures, how to incorporate this concept of resonance when it's necessary, and then how to use formal charge to evaluate between multiple structures, which is better. That was the lesson. There's some homework on it tonight for you to start looking at. And then we'll see where we're at tomorrow. I don't want to over push you, but we do need to give a little bit of a jolt tomorrow just to get you started on the Vesper stuff. Yeah?
Where are these at?
What's these? Hang on to them because I'm not done talking about them yet. There's still examples off of them I want to play, so hang on to that and we'll go. Thank you. You're going to have to jump around in the homework because I stacked the last 2 assignments onto tonight. Don't try to do it all. Just kind of pick and choose some. See where you're at.
Lesson ends.